right. Hello, everyone, and welcome to this week's Digital Manufacturing Talk. My name is Tyler Fenhouse. I'm the marketing manager for Symphony AI Industrial, and we've got a great digital manufacturing talk lined up for you today labeled AI to improve rotary kiln operations in metal and cement application. As you may know, Symphony AI Industrial is a leader in industrial AI solutions and digital manufacturing, plant performance, optimization, and connected worker. Symphony AI Industrial is a Symphony AI vertical. There are several Symphony AI verticals. You can see them there on your screen. And we are one of the largest, if not the largest, enterprise AI companies with more than 1,600 customers and 3,000 employees. We are on the Teams format, and we've got a lot of people signed up today, so you will be muted throughout the presentation, but we still want your questions. In the chat, you can ask Sudhanshu, your presenter today, whatever questions you may want to ask him, and he will answer them at the end of the presentation right here live. So make sure you're typing those questions in the chat as we move along. Also, be on the lookout for poll questions that we'll be asking you periodically, and that'll kind of guide the presentation today. All right, you didn't sign on to listen to me talk all day, so I'm going to hand it off to Sudhanshu, and we're going to get this talk started. Sudhanshu, go ahead.
Okay, thanks, Tyler. Good morning, good afternoon, everyone. So today's topic, as Tyler mentioned, this rotary kiln and its application in industrial processes. So we're going to cover some topics. What is rotary kiln? So some of you are not aware or have not had chance to work on rotary kiln. So we'll cover some basics and also look into some industrial applications where rotary kiln is used. And then two use cases we'll cover. One application of AI in direct reduced iron process, which involves rotary kiln. And second use case, we'll look into free lime reduction in cement kiln operation. So let's get started. But before we get into our use cases, over to you, Tyler, for a poll question.
All right. You should see the poll question there. Can you see the poll question, Sudhanshu? I'm not quite sure why.
Not yet.
Okay, let me launch it again. I'm going to reopen it. Okay, people are voting. Okay, so sorry about that. Describe your familiarity with rotary kiln. I work on a process involving rotary kiln. I am familiar with rotary kiln. I am not familiar with rotary kiln. So go ahead and click to vote. It looks like about half the room is voted. So go ahead and get those votes in if you can, and that'll kind of, again, guide this presentation. Okay, I will leave this open for a couple more seconds. We've got 7 stragglers in the room. Go ahead and click to vote. All right, so it looks like 27% work with a process involving rotary kiln, 27% are familiar, and 45% are not familiar. Back to you, Sudhanshu.
Thanks, Tyler. And if you are not familiar with rotary kiln, we'll cover some basics in next slides. So what is a rotary kiln? And as a definition goes, a rotary kiln is an inclined rotating cylindrical high temperature reactor. So wherever rotary kiln is being used, it's a kind of reactor where many reactions happen inside it. And as name suggests, it's keep rotating with a low RPM, as well as it's inclined such that material can move from one end to another end. So what you see here is a typical kiln in cement manufacturing process, but very similar kiln operations are also used in other industrial processes. So if you look at what are other applications, so of course cement manufacturing, where we produce clinker and that uses a rotary kiln. We get into iron making industry, and iron ore is being converted into pellets, and it goes through multiple operation which we call induration process: drying, heating, cooling, hardening those pellets, and that happens through a rotary kiln operation. And again, is in iron manufacturing industries, a direct reduced iron process, that is a making of a sponge iron from iron oxide, that involves a rotary kiln process. And one of the use case we are going to cover today will be on DRI process. Again, in gold industry, when we do carbon in leach process and we want to carbon regeneration, thermal desorption process happens, which involves rotary kiln. Calcination of limestones also involves rotary kiln. So there are many applications in industry. There are which we know, and we'll be covering two out of it, one from cement manufacturing and another for DRI process. So let's get started with our first use case, the AI application in direct reduced iron process. And as you could see here that we have a rotary kiln here in the DRI process. So we are going to cover a brief intro to a DRI process, as many of you might not be aware. So give us some background. And then we'll look into the AI applications and opportunities in DRI process. And at the end, we'll also look what kind of benefits could be achieved by applying these kind of solutions to the rotary kiln process. So, as direct reduced iron process, as name says, it's involved reducing iron oxide into metallic iron, and that's the sole objective of DRI process. So here is a very high level schematic of DRI process, and at the center, what you see the kiln, which is a kind of heart of this whole process. And the feed to the kiln system is iron ore pellets, which is in form of Fe2O3 and Fe3O4, hematite, magnetite. And since the reaction which is going to happen inside the kiln is a reduction reaction, you need some reducing agent, and for that purpose, coal is being fed to the to this end, feed end of the kiln. And also, since this coal does not go through entire kiln, it gets consumed somewhere in the middle. There a injection coal from the rear end of the kiln is also injected with high pressure injector to cover the second half of the kiln, such that there is a good availability of carbon in the kiln, such that reduction process happens. So carbon is used as a reducing agent, and as well as to provide heat, because the reactions happens here is a high temperature reactions. And of course, if we want to produce heat by burning coal, we need air. So combustion air is also given to this kiln. And as you could see, there's a primary air which injected from rear end using a central burner fan. And there are secondary airs which are being injected on the using a tube on the cell of the kiln. And finally, when this ore goes here, and the output, we get a reduced metallic iron, which is also called as a sponge iron. So that's the very high level process schematic here. So we'll look into what are the parameters impact overall reduction. So objective here is to maximize the reduction in the kiln, that is the reaction happening. So we have highest percentage of metallic iron when it exists from the kiln. So if you look at kiln temperature, and these are the phase diagram, what we see reactions, how reactions proceeds. And it's very clear, as you could see, that high temperature, when temperature is high, we have a better reduction. And low temperature reduces reduction. So we want high temperature in the kiln such that we have a better reduction. But also high temperature causes uh, uh, accretion formation. That is, as particles in the coal, they come together and form a ring, and that inhibits the flow of material through the kiln. So that's the problem. So this becomes a kind of optimization problem, where we want to keep the kiln temperature in the right range, not too high, not too low, so operations could be smooth. Again, second very important parameter is the kiln retention time, and it's evident from this graph here that reduction increases as material lives in the kiln for longer. But we also know that uh, uh, if you keep material longer in the kiln, our overall productivity will be down. So again, we need to optimize it. We have to be optimal retention time in the kiln, so we get better reduction as well as better throughput through the kiln. And then last but not least is availability of carbon and oxygen. So as I mentioned earlier, that carbon is a reducing agent which is being used in this process, and that comes from the coal, and it has to be available throughout the kiln such that reactions continue from start of the kiln to the end of the kiln. And of course, oxygen is needed because we also need heat, and all this combustion of carbon is giving heat to the overall process. So we could raise the temperature of kiln. And if you have a low carbon to iron ratio, that will cause lower reduction. But also, if carbon to iron ratio will be very high, that is not very economical, and also it will can cause very much temperature control problems. So, so what we learned from these three type of kiln temperature profile, retention, and availability, that temperature control and uniform carbon distribution is very important for overall better reduction. So we look into a little bit more detail that what are options we have to do temperature and carbon control in the kiln, and what are the challenges in this process. So again, this is a schematic of a kiln, and we see a preheating section. Before that, iron ore with feed coal and some of the dolomite is being fed. It goes through the kiln, and then we get an injection from the rear end where we inject coarse coal as well as fines coal. And reason for doing a mixture of coarse and fines coal, that making sure that injection gets distributed evenly throughout second half of the kiln. So fines particles will fall at the near the injection point, but the coarse particles will travel further into the kiln. So we have a better distribution of coal particles inside the kiln, and that will provide us a better reduction as materials flows through uh, feed end to exit end. So when we talk about measurements on kiln, and temperature is one important measurement we would like to have, since we have seen that temperature impacts reductions significantly. So there are thermocouples installed on the cell of the kiln, and they measure the temperature of kiln in real time and call as NRT, normal response temperature. And also we have air tubes which allows secondary air, and since air helps combustion and control temperature, so that is necessary here. So so in NRT is continuous measurement, but also in these processes there are manual measurements done time to time. It's called QRT, and those are being done by inserting a thermocouple manually inside the kiln, but these are intermittent measurements. So every 4 hour, every 6 hours, somebody goes physically and then measure these temperatures. So here NRTs are the problem what we face with temperature control is unreliable NRT measurements, because those sensors, thermocouples, get coated with ash particles, and once that happens, the measurements are not accurate. And that's why the QRT is being taken to understand the real temperature of different zones of the kiln. But again, QRT is not continuous; it is being taken manually in intermittent way. And of course, the air profile management is another challenge here. So we'll talk about more how AI could help in all these problems. The second part is carbon control on the kiln, and we see it is being controlled by these coarse particles, fine particles, injections, or feed coal. So these are the three ways of injecting carbon in the kiln. And of course, the injector pressure is another key parameter which helps how far the injection coal will travel inside the kiln. So challenges with carbon control is variation in coal fed to the kiln, and very often fixed carbon, moisture, volatile matters keep changing for the kiln, for the coal being fed to the kiln. And another problem is particle size variation. So this coarse and fines particle size distribution changes, and that impacts the distribution at the rear end of the kiln. So we'll also look into how AI could help mitigate some of these problems. So let's get into how AI-based models can be used and improve overall the process. One thing can be done is forecasting the product grade. So the objective here is that how much reduction is happening, and we can know upfront that how it is going to be next 8 hours, 6 hour. That is material which is already traveling in the kiln. Operator can take action to improve the reduction in the rear end of the kiln by controlling the coal injection. And we talked about that NRTs are not very reliable, so you could have a AI model, ML model, which could estimate the reliable kiln zone temperature, which is very important for whole operation. And coarse and fines particles needs to be optimized, since there are always a variation of particle size as well as the coal properties, and that's where this optimizer, AI-based optimizer, can help. Uh, and it could help recommending what could be primary, secondary air, as well as at the end, it could look into entire process parameter altogether and see if certain parameters are going anomalous. There's some problems developing in the kiln process. So AI can do that as well. So let's start a little bit deeper into these solutions, what is being implemented, and how the result looks. So we start with the continuous quick response time QRT forecast. So we see that NRTs are not reliable. As I earlier told, that there's a accretion happens, and that makes thermocouples not giving right results, and manual results are available only intermittently. Intermediate operations runs based on the experience and guess by operators. So here is opportunity to do a model which can use online NIT measurement, which is not very accurate, along with the QRT manual data, which is not continuous but accurate. So using these two models self-tunes itself and try to predict a good result in between. And so you see here an example that one of the sensor, actual NRT, it is giving a temperature of 200 degrees centigrade, which is completely false. It kiln temperature never be 200 degrees centigrade. So this temperature has heavy accretion coating on this thermocouple has heavy accretion coating on it, and that's why it is giving very low reading. But you can see that actual QRT is on around 1100 range. And then when we look at the forecasted QRT, which is a forecasted or estimated one, and so it also estimates and forecasts that how temperature will vary in next 1 hour time period. So and we can see that these two are very accurate and very close, the manual QRT measurement as well as forecasted QRT, which is done by the AI models. The second, we'll talk about the FEM forecast, that is product grade metallic iron percentage. And it was done for 8 hours in future. So this is again being done through a lab. So samples are taken and then sent to lab for analysis, and then they come to know after a couple of hours what is the produced grade at that point, how much reduction kiln is producing, and there's always a lag, so actions could be delayed. If you could do a good forecasting here, and we see that grade is dropping, that is reduction is dropping, action could be a proactive action could be taken, and that's why this model is being used. And architecture of model is along a sort of memory network LSTM, which is being trained on the historical data. For example, many measurements, temperatures, what we had from the plant. And then once model is operationalized, it uses the live data to forecast the metallic conversion, the metallic reduction in iron at the end of the kiln 8 hours in advance. And here is a comparison of actual reduction, which is being measured in lab, and then one the predicted one, forecasted one. As you could see that this very close and following each other. We had run these models for quite long time, and then looked at the accuracy of the models, and within 80% of time, we had accuracy where results were within within plus minus 2% of actual values, and almost 100% time it was directionally accurate. So when it, forecast was that grade is going to drop, it always dropped, and when it told grade is going to be up, it always go up. So very good forecasting model we could achieve, and being helpful to customer, knowing in advance what is going inside the kiln. We talked about the fine and coarse coal problems, so that is being done to ensure that there is a good distribution of carbon in the kiln. And but if particle size variation happens, you could see here an example that particle size, the mean particle size, how it is changing over time, and also the properties of coal changes. So coal fixed carbon variation. So you see there's a quick dip into the coal fixed carbon, and these parameters impacts how much coal, coarse coal or fine coals to be injected. So for example, say we have a lower carbon in incoming coal, then we need to feed more coal to ensure that the carbon percentage is same, carbon amount is same in the kiln, which could reduce the iron being fed to the whole process. So how it is being done? So AI model identify the best operating condition based on the historical data. So it identify when whole operation was running good, and on that basis, it gets and it also gets the information from lab, what is the fixed carbon, moisture, size. And then based on variation in feed, it recommends the fines and coal set points such that size distribution is close to the best operating range. So, so there's a baseline being done, and based on current conditions, it try to predict that what these set points should be, so we can achieve the best operating conditions. So this the underlying model is being set up. And you could see here how it changes. So since most of the time we have to maintain fines and coarse coal, the overall carbon in the kiln accurately. So there is a fluctuation. So when coarse coal goes high, fine coals comes down. The primary and secondary air advisories, and these are being done because we want to either increase or decrease the temperature. So mostly maintaining the temperature of the kiln zone. And here you could see that this is the primary air central burner fan, and this impacts rear end of the temperatures to a large extent. And if those temperatures are going high, then there is a, you could see the recommendation to reduce the fan speed. So you can cut the air and reduce the temperatures. And sometime we have the secondary air, which is on the cell tubes. And at these cases also, if you see that temperature is going high or low, in the particular zone of the kiln, a decision could be taken to cut the air or add the air if you want to increase temperature. So those kind of control is being done, and model works in the background and give these kind of advisories. And finally, as we talked about that, this is whole big process, and we want to look at whole process holistically and see if it is something is going wrong, and that's where the skill process anomaly detections comes into picture. And the approach here, that model learns the best operating data when kiln was running fine. It was producing best reduction, that is required grade of more than 80%, and learns those optimal operating parameters. And then it analyzes the real-time data and detects any abnormality in that data, highlights those abnormality along with the parameters causing it. It also can generate alerts, lists probable causes and actions to be taken. So here is an example that plant is running fine, and then we see an anomaly being developed here, and we could see that what are the parameters causing this anomaly, and the fines, what you see here is one of the major contributor, and you can also see in the right side here that fines percentage being dropped in this case, and that's the causing the anomaly. And it could generate these kind of warnings, alerts, and give causes recommendations as well, which could help mitigate the problems. So overall, if you look at this whole process, we could see the benefits. Product FEM forecast enables operator to take early action to avoid grade drop. So you know upfront that something going to be wrong, and then some corrective actions can be taken. And knowing reliable kiln zone temperature gives better control and better reduction, overall better product. And finally, optimize cold feed ensures quality product and reduce coal consumption. Air advisories again helps to uh, control the temperatures better, which is very important for overall reduction, as we have seen earlier. The anomaly detection, as we see that it looks for 100 plus parameters all together and highlights if any problems are developing, and then also gives prescriptions about them. So this is about our first use case, and now we can get into the second use case, which is free lime reduction in a rotary kiln, and this is pertaining to the cement industry. And if you are from cement industry, you might already know that the kiln is being used to give raw material to a clinker formation. And there are again many reactions happen, starting with drying, calcination, sintering, cooling. So all goes through this kiln, and finally you get a clinker which has uh, dry calcium silicate, dicalcium silicate, aluminate, ferrite is major composition, but it also gets something called free lime, which is undesirable, and it undermines the quality of cement, and that has to be minimized from this process. So we look into how that can be done using AI. So if you want to look at this free line and all process parameters, so here is some correlation chart. As you could see, that free lime is very much heavily positively correlated with the dicalcium silicate. So whenever a dicalcium silicate is high, we are seeing that the free lime is also high, and it's negatively correlated with tricalcium silicate. So when tricalcium silicate goes up, free lime comes down. Other parameters like lime saturation factors, burn temperature also have very heavy correlation, as you could see with the free lime. So we can see there are many process parameters which impacts and very much related with free lime. So we could control them to have a better control over it. And in this particular plant, if you look at historical distribution of free lime, you could see there's a right tail where it goes even up to 4% sometime, and its quite percentage is above 2%, which is and a plant desired it to be all less than 2%. So here's the opportunity to reduce this right tail, what we see. And if we do so, and then after correction, we could see overall 10% mean reduction of the lime in the plant, and distribution looks like this. So the solution what we have developed for it is uh, uh, a soft sensing model. And why this soft sensing model was developed, because operators had tree line reports being given to them every 4 hours. So they could take any action once in 4 hours once they have a report that how free lime they are getting in the clinker, but that is delayed and that is lagged, and more could happen in the 4 hour period. So soft sensing is an AI approach which could be applied to predict the free lime in real time using the process parameters of what we have seen in previous slides, where there's a very good correlation with some of those parameters. And we have done these predictions and tested on our testing data, and this is quite good accuracy of model, as you could see, 86%, and also it tracked pretty well the variation of actual versus predicted. So once we have this soft sensing model in place, which is artificial neural network model, we can start we can have an AI optimizer which could use these predictions, for example, free lime, burn zone temperature, and C3S, which is coming out of this model with all these inputs and the left side, what you could see. It could be this is limited inputs has been shown here, but in actual conditions, there will be more inputs to these models. And once we have this in real time, and we know in what range we want to control the free line with other constraints, AI optimizer can set up advisory which could give which gives the uh, set point advisory, for example, say what should be a raw meal composition or lime saturation factor, cold feed, raw feed, and sometime air. Although kiln RPM is not something being changed very frequently, but that was also kept as a part of advisory. And that is this model is being run, fed to an operator which can key in all these information back to the DCS, all the set points to control the free line distribution. So let's look at the what are the benefits of free lime reduction. And free lime reduction, if you see here, there's this very much strong negative correlation with the tricalcium silicate. So whenever free lime is high, tricalcium silicate is low, and whenever free lime is low, tricalcium silicate is high. And as we know that tricalcium silicate provides early strength to the high early strength to the cement, and it's desirable to have a high C3S to C2S ratio. So, so reducing a free lime gives that a benefit. Also, it's a known fact, more than 2% free lime in clinker increases the expansion risk of concrete. So it undermines the quality of cement significantly. By reducing it, we'll have much better quality. And also, here you see the 10% reduction can give you a tricalcium silicate increase by 2%. And since a ratio of tricalcium silicate and dicalcium silicate is being maintained, it allows to induce some fly ash or low value product mixed into cement and have same quality. So basically, it's helping to overall improve the cement production without compromising on quality, and also giving better quality cements. It's the benefits applying these kind of solutions to the cement industry. So to summarize what we have gone through today, rotary kilns are widely used in metal, cement industry, as well as many other industries. And major challenges in operating kilns are temperature control, fuel, air control, which could be addressed through AI-based models, and that could bring value to the industries and operations. So here we stop for next poll question. Over to you, Tyler.
All right, we do have one last poll here before we get to our Q&A, and a couple questions did come in, Sudhanshu. So if you could, start scouring the chat and take a look at those, starting at the bottom, so you can kind of see what's coming down the pipeline. I'm going to grab the reins here for a second right after we get done with this poll question. But based upon this presentation, AI can be used in improving plant processes and efficiencies, can be used at your company, can possibly be used at your company. Not sure if it can be used or they cannot be used. Looks like a good chunk of you have voted. Get your votes in if you have not. And I'll leave it open for a couple more seconds and then we will get to your questions. All right. Um, all right, let's take a look. So it looks like Sudhanshu, 40% say that can definitely be used, 53% can possibly be used, and 7% are unsure. All right, fantastic. I'm going to go ahead
Yes,
and share
yes.
my screen here for a brief moment. So, folks, we appreciate everybody here making it to the end, and we appreciate you attending our famous digital manufacturing talks. And we do have more of them booked out all the way up until the end of December. So, every week, usually the same time on a Thursday, sometimes on a Wednesday, but you just set in with Sudhanshu. But we have topics covering connected worker, digital manufacturing, vibration monitoring. You're going to want to come. We've definitely got a digital manufacturing talk for you. So like I said, Thursday, usually Thursday, same time. And if you want to see what we've got coming down the pipeline, all you need to do is go to symphonyindustrial.ai, go over to resources, drop down to webinars, and it'll bring you to the digital manufacturing talks page and you can register right there on the page. So we hope to see you at another talk very soon. That being said, Sudhanshu, if you've taken a look at the chat, I don't know, do you want me to read them to you or do you want to go ahead and read them off and answer them?
Yeah, I will. I can see the questions, and I will go through at least in next 7 8 minutes. Will answer as many as I can.
All
So the
right.
question here is QRT done in the kiln, and if so, how? So yes, in this particular case, QRT is done on the kiln, and it was a manual operation where operator goes with a handheld thermocouple, and there was opening in the kiln. He inserts the thermocouple inside the kiln and takes the temperature. So that's the way it was being done in this particular case. Uh, Second question is, could you elaborate more on how the model retunes itself every few hours? So I think this question is pertaining to NRT, continuous NRT prediction and forecast. And so we know that QRT temperatures are very reliable because it's taken manually and always thermocouples are clean in that case. So we can we have always a ground truth that where we are every 4 hours, and we also have these NRT temperatures which are being measured continuously, but they might not be very accurate. So now we have accurate measurements every 4 hour and something continuous but not so accurate always. So we fit this QRT and NRT data using historically. So we build a base model. That base model does the prediction, but also if we see whenever QRT measurement is available, which is accurate measurement, and there is a gap, we add that bias to the model, so it retunes itself and adjusts to have predictions, good predictions when next time it does forecast or estimation. So that's how that model works on very high level. Please email the video link. Sure, we'll do that. What features were selected for LSTM model? Did you do PCA before LSTM static data? Did you categorize with time series? What was the autoencoder shape matrix? And what was the computational cost effort in terms of iterations? So yes, we did do feature selection, although not PCA in this case, but domain-based feature selection we have done, where we have gone through and selected certain parameters which are important for FEM, and we use them. And uh, we uh, we had we had a LSTM model. It was not auto encoder, but deep network. We have used three layers and one input layer, one output layer. So if you'd like more detail on it, we could connect and I can give you more architectural detail of LSTM. Computational cost, it's not much because we're using certain around 20 parameters to do this forecast, and we use around year of data to train the models. So that wouldn't be very significant. Any decent computer can run and do those predictions and forecast. Um, what was the model in anomaly detection, isolation, forex, K-means, DB scan? Did you cover the girth, gear, riding rings issue as well through vibration? In case you detected anomaly, how did you find the time to failure? So here we use autoencoders for anomaly detection. We use PCA, and we also use some of the techniques like KNN, K-means, as you mentioned, and we take ensemble approach. We take results from all these, combine them together to have more stable outputs. And in this particular case, we are more focused on process, not on the mechanical failures. So we didn't take girth gear or vibrations into account, but that can be done. So if objective is to look into the machine failures or and all, we could take those parameters into uh, our models, and then it could predict.
All right,
This
fantastic.
type of
Oh, sorry. Is there more?
Yes, this type of problems are typically solved by model predictive controller. Have you compared a performance against traditional MPC performance? Could highlight how it is different from MPC solutions. Yes, so these kind of problems, yes, technically can be solved through the MPC, but as you know, MPC does very linear kind of prediction of forecast, and for a very short period, because linear these are complex processes, and you cannot forecast accurately for longer period, and then it does a recommendation on based on that. So the advantage with a AI-based process that we could forecast better than linear, so we can have a non-linear models which can do forecast. And second biggest advantage is adaptive. So AI models could be very adaptive. It could learn from the changing process and incoming data and keep it up to date. And MPC controllers, so you tune it for one time, you make a DOE and all the step changes and do that. And it works 3 months good, and then after that start deviating. So many times we have seen customers stop using after a few months MPCs. And so AI-based models have some edge there where they can up to date themselves and become better as they go. So there
Okay.
are a few more questions. I'll take maybe two more.
Okay.
Uh,
Or can you, I don't see any more questions. Can you, maybe my interface is messed up.
yeah, so I think one last one. Could predictive maintenance also improve free lime reduction? If so, how? Which assets in the kiln process contribute majorly to free lime? So we we I can't comment on that whether predictive maintenance can improve free lime because our focus was more on the process side. So we were looking into what process parameters impact free lime. So that is feed quality, as well as we have many process parameters, temperatures in kiln, and while doing analysis, we found that there is a good correlations, and that impacts the quality of that is free lime and the clinker. So definitely the process what we saw impacts the free lime, but I'm not sure about whether it maintenance, predictive maintenance, or equipment's not working well could do that. We have not done that analysis, but it might. We can look into it.